Hello there. In the last video we talked about a numerical measure that will pretty much tell you the variation between two numerical variables x and y. And we referred to that as the covariance between x and y, which is calculated by calculating the sum of the products of the differences between the values and their corresponding means. So one of the properties of the covariance was that the covariance was not bounded above or below. That is, you can have a covariance of a million, a billion, or a negative trillion, or something even small like 0 or 5. Now, another downside of the covariance in terms of interpretation is that the units may seem slightly complicated. Because when you have x and y and they're measuring different things like heights or weights, then the product is the product of their unit of measurement as well. So sometimes this may be slightly confusing to sort of understand. So pretty much another numerical measure that can tell you the correlation between variables is what is called the Pearson correlation coefficient, which is going to be the focus of this video. So the Pearson correlation coefficient. So the Pearson correlation coefficient is probably one of the most common linear regression calculations that people use. So this is going to be the Greek letter rho. So this is the correlation coefficient for the population. This is going to be the covariance of the population divided by the product of the standard deviations of the populations of x and y. And then the sample statistic R is going to be equal to the covariance of the sample of x and y divided by the standard deviations of the corresponding samples sx and sy. And also, if you want to calculate these in Excel, you can calculate it via the expression Pearson of x and y. And this is going to be used for either one of these. And I won't go through the algebra, but if you're interested, I leave it as an exercise to show that the results actually give you the same thing, regardless if it is a sample or a population. So let's discuss a couple properties before we do an example of this. So one of the main properties is that this thing, I'll use rho or r, these things are always between -1 and 1. So let's pretty much map out a little chart of how to interpret these numbers. So -1, 1, 0, and we'll put some tick marks in the middle. So if you have a Pearson correlation coefficient of -1, this is what is going to be referred to as a perfect negative correlation, and at 1 this is going to be referred to as a perfect positive correlation. So when I say perfect positive versus perfect negative, I'm referring to the graphs where if you do pretty much a line of best fit to all these data, it's going to pass through all the data values. So everything to the left is a negative linear correlation, and everything to the right of 0 is of course a positive linear correlation. And some people refer to this region as the strong negative, and this region as the weak negative, this region as the weak positive, and this region as the strong positive. And as far as what these numbers are actually equal to, whether they're 0.5, 0.8, 0.95, it really depends on the application, and it's pretty much a subjective thing depending on what you're actually measuring. And of course, 0 corresponds to no linear correlation. And this pretty much goes back to the case where you have something like this. All right, so let's go through a example of how to calculate this by hand. All right, so which data set has a more stronger linear correlation? So I'm going to give you two data sets to work on. So S is going to comprise of 056, 1076, 1281, 897, and 9726. And another sample T is going to be 9373, 565, 7877, 4770, and lastly 1582. And if you want to take the time to sort of get these data sets in Excel before we move forward, please take the time to pause the video and input them. So once you get this in Excel, you can calculate the covariance of S to be equal to covariance.S of x comma y. And that's going to come out to negative 1339.15 approximately. And similarly, the covariance of T is going to be negative 37.4. So if we do the Pearson correlation coefficient for this set, R, so RS and RT, you're going to get that this is going to be equal to negative 0.8863 and negative 0.0392. So these are our Pearson correlation coefficients for our samples. And then we compare them. So we pretty much ask ourselves which R is closer to plus or minus 1. So as we see that RS is closer to negative 1 than RT is to negative 1, so that means what? So that means S has a stronger negative linear relationship than T appears to have. And some people even consider another numerical value, which is called the R squared value. So the R squared value measures the strength, not direction, of the linear relationship. So all we're going to do is just square these R values that we have. So that means R squared of S is going to be equal to negative 0.8863, the quantity squared, and R squared T is going to be equal to negative 0.0392, the quantity squared. So that means once we square that, what do we get? So 0.8863 times 0.8863, that's going to be equal to 0.7854. And R squared T is going to be equal to 0.0392 times 0.0392. So that's going to be equal to 0.0015. So these are our R squared values. So remember that R squared is always in between 0 and 1. 1 is going to correspond to a perfect linear relationship, and 0 is no linear relationship at all. So again, we see R squared S again is closer to 1 than that of R squared T. So that means S has a stronger linear relationship than T does. And of course, R squared is sometimes the more commonly used one. Some people use R, but R tells you the direction, and R squared pretty much tells you the strength. Both pretty much tell you the same thing, but R squared you can't tell if it's positively or negatively correlated. But this is pretty much a summary of the R and R squared Pearson correlation coefficients, how to interpret them, how to calculate them, and pretty much what you can get from them once you calculate them. And of course, I always recommend that always graph your data beforehand. because just looking at these numbers may give you some misguided ideas, because if you actually calculate the Pearson correlation coefficient for a data set such as this, then you're going to get an r-squared value of approximately equal to 0. Just because it's closer to 0 does not imply that there is no trend. Does not imply that there is no trend. It does not imply this. The only thing that it does imply that there is no linear trend. That is the only thing that this does imply, because clearly there's, this could be possibly a normal distribution for all we know. But if we do like a correlation coefficient, that's going to come out to approximately 0. So always keep in mind when you're going to do some linear regression methods, look at your data first and then do some numerical analysis methods, whatever you have. And that's pretty much a summary of the Pearson correlation coefficient.